Hello everyone, welcome to this class. In this class, we're going to continue with parallelogram and related quadrilaterals. Let's start defining them. First, what's a parallelogram? It is a quadrilateral that has both pairs of opposite sides parallel. Look at it. This is a diagram. You can see that these sides are the opposite sides. These are the opposite side. This is parallel, and these are the next opposite side, and both of them are what? Parallel. So what's a rhombus? Is a parallelogram with sides of equal length. Now what this rhombus is like this, but in this case you can notice that this length is obviously longer than this, or in the case of a rhombus you see that the four sides are equal, which we indicated with this our sign here. The third one, a rectangle. A rectangle is a quadrilateral that has its angles right angle. So this is a rectangle. We're already very used to this figure. Where they meet are all right angles. While a square is a rectangle with sides of equal length. So this square is just a rectangle, but just that the four sides are equal. Look at the rectangle, you can see that this side is obviously longer than this side. So let's go to the next theorem that we're going to do in this chapter. So theorem 6 simply states that in a parallelogram, the opposite sides are equal and the opposite angles are equal. So what it's trying to say is that this is a parallelogram. This side is equal to this side. This side is equal to this side. And opposite angle, these are the opposite angles. These are the opposite side, and these are the opposite angles. So this angle is equal to this angle, and this angle is also equal to this angle. So let's prove that in this class. So to prove this theorem, I have to draw a diagonal by setting this angle here and this angle. So let me call here A, B, C, D. And when you are labeling all these things, follow one direction. You can follow this direction, you can follow this. Don't come and write A, write B, and if you scatter it that way, you mess it up. You mess it up. So, since this is a bisector, we already know that this is equally divided. But let's not go to that route. Now, this is a parallel lines, and we know that when a line joins two parallel lines, we have an angle here. We have another angle here. So let me call this x1 and y1. I'll call this y1. Let me call this x1 and y2. Let me call this y1 and x2. Are we together? First thing we are going to know is that this AB is equal to, we are trying to prove that AB is equal to CD, which is from our first theorem, that this is equal to this and that is equal to that. AB is equal to CD. Also, we're also trying to prove that BC is also equal to AD. Are we together? The second thing we wanted to prove is that angle B, which is our opposite angles, is equal to the opposite angle, which is angle D. Also trying to prove that at the same time that angle A is equal to angle what? C, which is opposite to it. The first thing we are going to do now, let's apply our laws of congruent triangle. These are two parallel lines. So when a line joins two parallel lines, it forms what we call an alternate angle, which we've done in our previous class, that alternate angles are always what? Equal. So first thing we are going to do is x1 will be equal to what? X2. X1 is equal to x2 because of what? Alternate angle. At the same way, we also have another alternate angle here, showing us that what? Y1 is equal to what? Y2. The same reason, alternate angle. Now let's apply our law of congruent triangle. Since we know that, let's take this triangle ABC. This is one triangle, and another triangle CDA. First, we already know that these two angles Are we together? We already know that from our congruent triangle. When remember the law that says when you have two angles equal and a corresponding side, they are congruent. So since this y is equal to this y1 and this x is equal to this x1, it's like this is equal to this, that is equal to that. So the two angles are equal, just that it's like this was flipped. You understand? And we all know that this side is equal because both of them are sharing the same side. So we can comfortably say that triangle ABC is congruent to triangle CDA. You understand? This angle, let's just say two angles. Remember when we were doing our congruent triangle, we were able to prove that if two angles are equal and one other side is equal, they are congruent. So let's use that one because you notice that this x is here and here. Some people get confused. The most important is that two angles of this triangle and this triangle are equal. This is equal to this equal to, and one side, which is this side that we know both of them are sharing, is equal. So it's congruent. So by so doing, this angle here becomes a corresponding angle. So, and we all know that since both of them are congruent, the third angle becomes corresponding angle. So angle A, I don't know if I'm messing this up. So for that, you can say angle B is equal to angle D because they are corresponding angle. I think we've proved that B is equal to D. So for us to prove that A is equal to C, we just add these two, And remind you, x1 and x2 are equal, y1 and y2 are equal. So when you add this and add this, whatever you will get here is also what you will get here. So let me say angle A is x1 plus y2. Y angle C is x2 plus y1. And we all know that this x1 plus y2 is equal to x2 plus y1. So from there we'll be able to prove that A is equal to what? C. So we're proving this and we're proving that. Excuse me. So since we're able to prove that these two triangles are congruent, it also follows that AB will be equal to CD since the two sides are corresponding, and at the same time AD will be equal to what? BC. Mind you, I can only say this because I know that the triangles are congruent. So the sides become corresponding and corresponding sides too are equal. For the little thing I want to clear here is, how do I know that x1 plus y1 is equal to x2 plus y1? I think let's do small trick here. x1 plus y1, right? Now in this case, x1 is equal to x2. So if you replace here with x1 and y2 is equal to y1, you can, okay, y1 is equal to y2, you can also replace here with y1. You can notice that this is equal to this. So let's not get it confused. So by so doing, we'll be able to prove theorem 6. So let's prove the next theorem, which is theorem 7. This law states that, theorem 7 states that the diagonal of a parallelograms bisect one another. What does it mean? It means let's call this A, B, C, and D. And let's call this center where they bisect each other O. It's trying to say that these two diagonals bisect. We all know what I said, what bisect. Bisect means equally divided. It means that where these two diagonals meet, it means that this A to O is equal to O to C. At the same way, B to O is equal to O to D. And we've already proven from our previous theorem that the two opposite angle sides are equal, and the two opposite sides, it's a parallelogram, so the opposite sides are parallel normally. So let me call here angle x1 and call here y1. Let me call here angle y2 and call here x2. So let's start proving it. So to prove this, first, these are two parallel lines. And remember we said when a line dissect two parallel lines, we form an alternate angle. So from here you can say x1 is equal to x2. alternate angle. At the same time, okay, let's say at the same time, y1 will be equal to y2, the same alternate angle. Now let's look at triangle AOB, triangle AOB, and triangle COD, triangle COD. What do you observe? You observe that the two angles here are equal for this triangle, this and triangle that, and then because it's a parallelogram, the two opposite sides are also equal. So we've already satisfied our congruent triangle. This is two angles and one side. So for that reason, these two triangles are congruent. And since they are congruent, any sides that look similar will be equal. We call it corresponding side. So we know this side corresponds to this side. So you can comfortably say AO is now equal to OC because they are corresponding. At the same time, this side also corresponds to this side. So you can comfortably say DO or BO, anyone you use is still the same, is equal to OB. So this proves that the diagonal of a parallelogram bisect each other. So if this is equal to this and that is equal to that, it means where both of them meet, they bisect each other equally. It means this bisect this line equally, and also this bisect this line equally. So let's solve an exercise. This is exercise 2E, number 3. We have in figure 2.36. This is figure 2.36. ABD. AB. I think I'm missing something. AB. So this is A, B, C, D. A, B, C, D. And C, D, E, F are parallelogram. So just know that this and that are parallelogram. So we are going to apply laws of theorems of parallelogram that we did in this class to it while solving this question. And ABEF is a straight line. If BE, this is BE, is 2 cm, and DC, this is DC, is 3 cm. Find EF. So you're going to find from here to here. So first, the theorem we did in our parallelogram, we were able to confirm that the two opposite sides of a parallelogram are equal. So this must be equal to this. At the same time, this must be equal to this, because we have been told that from the question, it's not we assuming that this is a parallelogram and this is another parallelogram. So since this is equal to this, here will also be 3 cm. And since this base is equal to that, here will also be 3 cm. So by the time you add everything, 3 plus 2 is 5, 5 plus 3 is 8. So the answer is 8 cm. Very, very simple. See you in the next class. If you have any question, drop it in the comment section. Thank you.